All right, welcome back. So I had to cut the previous video a bit short because I had to do something, but in the last video we talked about elementary matrices, and what those are certain matrices that you get from the identity matrix. And to form an elementary matrix, what you do is you take one of the elementary row operations and apply it to the identity matrix. And if you do that, the result, the matrix that you get is called an elementary matrix. And I gave 3 examples of elementary matrices, one for each of the 3 different types of elementary row operations. And in the previous video, I mentioned that elementary matrices are sort of like the atoms of all invertible matrices. And well, what do I mean by that? So that's what we're going to talk about in this video. So one of the reasons why elementary matrices are significant is this theorem. So the theorem is, suppose that you have an m by n matrix. Let A be an m by n matrix. So in other words, just any matrix whatsoever. Any elementary row operation on A, that says any, may be carried out by pre-multiplying A. So what does pre-multiplying A mean? It means to multiply A by a matrix on the left. So multiplying A on the left. Pre-multiplying A by the corresponding elementary matrix. Okay, there's someone talking in the background. The iPad really picks up all background noise, so you can probably hear that person talking, but let's just, pretend that person isn't there. So let's just look at some examples. So let's say that A is this matrix 1, 2, 3, 4. Oh, God. Okay. So let's say that you apply an elementary row operation. Let's say that, for instance, you apply the operation that takes row 2 and replaces it by row 2 minus 3 times row 1. Well, what you're going to get by that is you're going to get this matrix 1, 2, 0, negative 2. Now, the theorem says that this matrix that you get is what you get if you take the corresponding elementary matrix and multiply it, and multiply A on the left by that matrix. In other words, the theorem says that this matrix 1, 2, 0, negative 2 is equal to what you get if you take A, so that's 1, 2, 3, 4, and then multiply it on the left by the corresponding elementary matrix. Well, what happens if you take the identity matrix and do this row operation to it? What you're going to get is you're going to get 1, 0, negative 3, 1. And you can check that it is in fact true, that if you multiply these 2 matrices, you do get that. Okay? So the theorem does check out in this particular case. So that's the type 3 row operation. Let's do type 1 and type 2. Excuse me. To verify that the theorem is true in this particular instance for this particular matrix. So for instance, let's take A again and swap rows 1 and 2. Well, if you do that, you're going to get this matrix 3, 4, 1, 2. And the theorem says that this is what you get if you take 1, 2, 3, 4, your matrix, your original matrix A, and multiply it on the left by the matrix that you get by taking the identity and swapping rows 1 and 2. Well, if you take the identity and swap rows 1 and 2, you're going to get this matrix, 0, 1, 1, 0. And yes, it is in fact true if you multiply these two matrices, those two matrices, that you do in fact get 3, 4, 1, 2. Let's do one more, a type 2 row operation. So let's say that you take this matrix again, and let's say that you multiply the first row by 5. So row 1 goes to 5, row 1. Well, what you're going to get is this matrix 5, 10, 3, 4. And the theorem says that this is the result also if you take 1, 2, 3, 4 and multiply on the left by the matrix, the elementary matrix corresponding to this row operation, which means, well, if you take the identity matrix and replace row 1 by 5, row 1, you're going to get 5, 0, 0, 1. And you can in fact check that, again, the product of these two matrices is in fact that matrix. And so that's what the theorem is saying. The theorem is saying that this is true. This fact is true no matter what your matrix A is. It doesn't even have to be a square matrix. It's still true. And one way to understand, I mean, you can check in a bunch of examples that's true, but one way of thinking about why this theorem is true is that if you multiply this matrix by this matrix, you can, when you multiply by a matrix on the left, what you're doing is you're taking linear combinations of the rows of the matrix on the right. So for instance, if I take this matrix A and then I multiply it by that matrix, the first row of the product is going to be 5 times the first row plus 0 times the second row. And that explains why you get 5 times the first row, 5, 10. That's not something that I'm going to emphasize very much though. Okay. So let's continue. So the next theorem is that every elementary matrix is invertible, and the inverse of such an elementary matrix is itself an elementary matrix. And again, I'm just going to illustrate this theorem by giving some examples. This is not a formal proof, but you can get the idea of why the statement is true just by looking at some examples. So let's just look at some examples. Let's do an example for each of the 3 different types of elementary row operations. So for instance, let's say that you have a type 1 elementary matrix. So it's a matrix that you get by swapping 2 rows of the identity matrix. It turns out that this matrix is its own inverse. If you multiply it by itself, you get the identity matrix. So for instance, if you take the 3 by 3 matrix that we saw by replacing rows 2 and 3, so you're going to get this. If you multiply this matrix by itself, you are in fact going to get the identity. And again, if you are familiar with this idea that when you start off with a matrix A, okay, and you multiply on the left by some matrix, the result you get, the rows are obtained as linear combinations of the rows of A. So for instance, in this case, it would be the first row of the product is 1 times this first row plus 0 times that row plus 0 times that row, and then you get this. And similarly, if you take 0 times, so you take the second row of the matrix on the left, if you take 0 of the first row plus 0 of the second row plus 1 of the third row, you get the third row. So the second row became the third row. And similarly, if you take the third row of the matrix on the left and then take the corresponding linear combination of the rows of A, you're going to get 0 times the first row plus 1 times the second row plus 0 of the third row, and that ends up being row 2. So that basically is the explanation for why the theorem is true in the case of a type 1 matrix. And so for type 2, let's just do an example. So let's say that you have this 5 by 5 matrix. But, okay, so you start off with the 5 by 5 identity matrix, but then you replace row 3 by C times row 3. Well, what can you multiply this matrix by to get the identity? You can multiply it by 1, 1, 1 over C, 1, 1. If you multiply that, you do, in fact, get the identity matrix. Right, so yeah, this is, in this case, I guess the 5 by 5 identity matrix. But you can see that this is true for n by n. Okay, and then the last one is type 3. So let's say, again, let's just look at a specific example. Let's take the 5 by 5 identity matrix that you get by replacing row 2 by row 2 plus C times row 4. Well, that's just going to put a C in the 2, 4 position. And you can check that this matrix has an inverse. You just change the C to a negative C and then multiply it out. Because the C is kind of an odd spot, maybe I'll put zeros just to indicate the location. The C is in the 2, 4 entry. And the same for the negative C. If you multiply them, you do in fact get the identity matrix. And so each of these 3 matrices is invertible, and you can in fact check that the inverse, right, these matrices, this matrix is an invertible matrix. In fact, the inverse of a type 3 matrix is a type 3 matrix. The inverse of a type 2 matrix is a type 2 matrix, and the inverse of a type 1 matrix is type 1. In fact, it's just itself. Okay, so these are very simple matrices to invert. Now let's apply this fact to understanding invertible matrices. So let's just recall that if you have an invertible matrix A, what do you get when you row reduce A? So you have a square matrix A, right? N by n matrix. You row reduce it and you get it to, let's say you get it all the way to the reduced row echelon form. What's the reduced row echelon form of an invertible matrix if you have an n by n invertible matrix? It's going to be the identity matrix, the n by n identity matrix, because you need to have a pivot in every row and column in order for your matrix to be invertible. And if your matrix is not invertible, what are you going to get? When you row reduce, well, you can get all sorts of things, but what do they all have in common? If you start off with a matrix that's not invertible, okay, a square matrix, and you row reduce, okay, you're going to see something at the bottom. The last row. You have a square matrix, not invertible, you row reduce, what's the last row going to be? It's going to be a 0 row. So, in fact, these statements that A is an invertible matrix and the statement that the reduced row echelon form of A is the identity matrix, these are mathematically equivalent. We're talking about the same types of matrices. So suppose that A is, so that's just the fact that hopefully you remember and you understand why it's true. So suppose that A is an n by n invertible matrix. Okay, by what we just talked about, when you when you row reduce, you're going to get the identity matrix. When you row reduce all the way to the reduced row echelon form. And remember that getting a matrix into its reduced row echelon form consists of applying a sequence of elementary row operations, just in a certain order to get the reduced row echelon form. So, and we just talked about how doing an elementary row operation, one way to think about what you're doing is you're multiplying A on the left by an elementary matrix. And so what this means is that there are elementary matrices E1 through EK such that if you start off with A and then multiply by E1, so that corresponds to the first row operation to get the identity matrix, and then you do the second row operation all the way to the kth elementary row operation. So that would be like multiplying on the left of E1, then E2, all the way to EK. This is going to be the identity matrix. So this is if A is invertible. Now, so these are all square matrices, right? They're all the same n by n. Okay, and we know that each of these matrices, E1 through EK, are invertible because that's what we just went over. They're elementary matrices, every elementary matrix is invertible, and so what we can do is we can multiply, let's try to solve for A. We can multiply by EK inverse Now, just saying that is not going to be good enough because remember, when you do matrix multiplication, the order, if you multiply on the left, you're not necessarily going to get what you get if you multiply on the right. So I should say that I want to multiply by EK inverse. Do I want to say on the left or on the right to get A by itself? I have this equation. I'm trying to solve for A. I need to multiply by EK inverse I need to multiply both sides by EK inverse on the left, right? So that will give me, do you see what I'm going to get? I'm going to get, maybe I'll use a different color. So you multiply this whole thing by EK inverse, multiply by EK inverse. So on the right, I'm going to get EK inverse. And on the left, what am I going to get? Well, I have this EK inverse times EK, and that's the identity matrix. And when you multiply the identity matrix by a matrix, you don't change the matrix. So what I'm going to get is I'm going to get EK minus E sub K minus 1 times E sub K minus 2 all the way to E1A. And now, what's the next step? We would multiply on the left by E sub K minus 1 inverse. So you repeat the process, and if you do that, you're going to get A on the left is going to equal, so I take EK inverse, I multiply by EK minus 1 inverse on the left, and I keep going until I get to E1 inverse. So now I see that A is equal to E1 inverse times E2 inverse all the way to EK inverse. And what I've done by doing this is I've written A, our general n by n invertible matrix, as a product of elementary matrices. Because remember, if EI is an elementary matrix, so is EI inverse. So E1 inverse is an elementary matrix, E2 inverse, all of these are elementary matrices, and A is a product of those. And so that's what I mean when I say that every invertible matrix, that's what I mean when I say that the elementary matrices are like the atoms of invertible matrices, because every invertible matrix A is a product of elementary matrices. And by the way, Also note, what would be A inverse? A inverse would be the inverse of this, which is ek minus 1 up to E1. It's the matrix that you multiply A by to get the identity matrix. Right, if you take this and you multiply it by A, you get the identity matrix. Okay, I have to go soon, but let's just do one quick example. I mean, what's nice about this theorem is that you can actually say what the elementary matrices are. So for instance, let's say that you write 1, 2, 3, 4. How can we write this as a product of elementary matrices? Well, I think you should try to figure this out on your own before looking up the answer. But very quickly, let's just see if we can figure this out. So first of all, you start off with 1, 2, 3, 4. What's the first step in the row reduction? The first step is to replace row 2 by row 2 minus 3 row 1. And what's the corresponding elementary matrix you get? It's going to be 1, 0, negative 3, 1, right? You do the same row operation to the identity, and then this is going to equal 1, 2, 0, negative 2. Now you take that, and then what's the next step in the row reduction here? You can, well, there's one of two things, but one thing you can do is you can multiply by, row 2 by negative 1/2. So if I multiply by that, I'm going to get, I'm going to get this. And now the last thing I need to do is I need to multiply, let's see, I need to do row 1 goes to row 1 minus 2 row 2. So I need to multiply by, so let's get rid of this now. If I multiply by the corresponding elementary matrix, row 1 goes to row 1 minus 2 row 2, that's going to be this matrix. And if I do this, I do get the identity matrix. I'm going to get the identity matrix. And so I have these three matrices. When you multiply it by A, you get the identity matrix. So therefore, A inverse is going to be, A, I'm trying to solve for A, is going to be the inverse of this. So it's going to be E1 inverse times E2 inverse. So it's going to be E1 inverse times E2 inverse times E3 inverse, which when you calculate it, we explained how to find the inverses of the elementary matrices. You're going to get 1, 0, 3, 1 times 1, 0, 0, negative 2 times 1, 2, 0, 1. So that's how you write A as a product of elementary matrices. This isn't the only way to do it because there's lots of ways to reduce A to the identity matrix. But this is one way to write A as a product of elementary matrices.